Welcome, engineers. Today we are looking at equilibrium of a particle. So when do we say a particle is in equilibrium? It's very simple. When the resultant of all the forces acting on the particle is zero, the particle is said to be in equilibrium. So anytime we find a resultant on a particle, and we know that the resultant represents a single force that can be used to replace all the forces acting on a particle. And if we find it to be zero, then that particle or that body is said to be in equilibrium. The sum of the components of the forces in any given direction must be zero. So if we have a body and we sum forces along the x and we get zero, we sum forces on the y and we get zero, and forces on the z and we get zero, that particular three-dimensional body is in equilibrium. And if it is two-dimensional, to summation on the x and y should be zero. So let's consider this two-dimensional body and look at how equilibrium is established. So I have some forces acting 20 newtons. I have another force of 10 newtons, and I have another force of 20 newtons. So here I will have a force of 25 newtons and another force of 25 newtons. Here I'm having 60 newtons. Pay attention. And I'm having 60 newtons. So how do we prove that this block is in equilibrium? First, we must check if the summation of forces on the x and on the y is zero. So first I'll check summation of forces on the x. So summation of forces on the x will be equal to, I'll choose my direction. So on the x-axis, I'll choose this way to be positive and that way to be negative. So any force in this direction is positive. Forces in this direction, they are negative. So first I have a positive 60 here, summation plus I have another negative 60 here, force, meaning summation of the forces on the x is giving me zero. Obeyed. So let's look at forces on the y. Is it up to zero, or summation, is it zero? Let's look at it. So summation of forces on the y, I will choose upwards direction to be positive and downwards direction to be negative. So I'll consider all the upward forces. I have 125 here, so a positive 25. I have another positive 25 force. They are all in newtons. Plus, let's look at the downwards forces. I have one downwards negative 20 here. I have another 10, negative 10. I have another 20, negative 20 newton. So let's look at it. This 25 and 25 will give us 50 newtons, plus the negatives will also sum up to negative 50 newtons, and I'm getting zero at the end. So 0, 0, meaning this block is in equilibrium, because the summation of forces on the x and on the y are zero. So anytime you're given a question to find the equilibrium, you check if the summation of forces on the x and y will be zero. And the force required on a body to bring it to a state of equilibrium is called the equilibrant. Equilibrant. The equilibrant is equal in magnitude. So let's look at it. Equal in magnitude but opposite in direction to the resultant of the original forces acting on the body. So anytime you have a body in equilibrium, and because initially it was not in equilibrium, a force has to bring it to equilibrium, and that force we call it to be the equilibrant. So in objectives you can be asked, and we know the nature of the equilibrant, that it is equal in magnitude but opposite in direction to the resultant of the original force. So assuming the body originally had a resultant of 60 newtons, To bring this body into equilibrium, the equilibrant must be opposite in direction and equal in magnitude. So meaning the equilibrant should also have equal in magnitude, 60 Newton force, opposite in direction, negative 60 Newton, so that the summation of these forces will be what? Zero, meaning there's no force acting on the body. So initially we had, let's look at this, we have this diagram. So if this is a 20 Newton force, let's say a 60 Newton force, and we found out that the resultant was this way. So this is the resultant, a single force that can be used to replace both these two forces. And we want to keep this body in equilibrium. We have to bring an opposite but equal magnitude what? Force to keep it in what? Equilibrium. That's what we got the equilibrant for this. So this force will serve as equilibrant to bring this body into what? Equilibrium. Let's look at a more practical point here. So the same thing, if I have a box where a pull of 100 kilonewton is pulling it along the x-axis. So it is being pulled. Anything less than 100 kilonewton will not stop the movement of this block or this thing. The only thing that can stop is that we have a force equal in magnitude but opposite in direction to this. If I have a force which is equal in magnitude but in the same direction as this one, this block would then speed up. So let's assume I have another force. Let's obey equal in magnitude 100 kilonewton, but opposite in direction. We didn't obey that. So they are all in the same direction. So the total forces acting on this block will now be what? 200 kilonewton, and the movement will be fast. It will move in the x direction this way. To keep it from moving now, the forces, they are what? 200 kilonewton. I should have a force opposite in direction and equal in magnitude to the resultant. So summation of this will give us 200. So I should have another 200 kilonewton force. So this block now is in equilibrium, because if you are summing forces on the x, and I will choose this direction to be positive, I will have a positive 100 kilonewton plus another positive 100 kilonewton. So this is in the negative what? Direction. Summation negative 200 kilonewtons. So in all, summation of forces on the x now will be zero, meaning the block is now in equilibrium. So simply we say that the equilibrant is equal in magnitude but opposite in what? Direction. Are we okay? Equilibrium of rigid bodies. So a rigid body is said to be in equilibrium if both the resultant force and the resultant moment acting on the body is what? Zero. So here, a rigid body, we included the moment. What is moment? The force times the perpendicular what? Distance. If it is zero, then the particle or the body is also in equilibrium. Are we good? So in some instances, we have to find certain reactions, and sometimes summing the forces alone will not give us a clear understanding of the equilibrium nature. Are we good? So we include the moment. For example, if I'm to find the reactions here, then it will be appropriate I take what? Moment. Because the weight of the car is also not what? Not known. So I'll get three unknowns in this figure if I want to solve for forces acting on this car. Assuming we know the weight of the boxes here, but the weight of the car is what? Unknown. So sometimes there are more than two unknowns, we will solve examples and you understand clearly what I'm saying. So it is very necessary we take what? Moment. So the moment point should also sum up to what? 0. And if moment summation is 0, then the particle will also be in what? Equilibrium. Are we good? So summation of forces is 0, as we have already explained, and summation of what? Moment. So let's talk a little about moment. So if I have, what is moment? I have a reaction here, RB. I have a force 20 newtons, and the distance between this and that is what? 3 meters. I have another reaction, RA, and I have another. So let's say the center is here. Now the width of this is W, and the distance here is also, let's say, 5 millimeters or meters. We have this to be 5 meters. Are we good? So here, how many unknowns? We don't know the reaction at A, we don't know the width, and we don't know the reaction. So if we are to find these three unknowns, first we can use summation of what? Forces to get one what? Equation. And then we can also use what? Moment to calculate for what? One unknown 2. Are we good? So with that idea, the moment summation should be 0 for the particle to be in equilibrium. Are we good? The moment should be 0. Moment, for instance, if I'm to take moment at point A, this place, then the moment of the weight will be the weight times, that's the force times the distance, the perpendicular distance. We will solve many examples on that. This will be the moment for this. If I'm to take the moment of RB, it will be the force RB and the perpendicular distance, which is what? 10 meters, to give me what? My moment. And we choose directions to clockwise and what? Anti-clockwise what? Movement. We will look at all that in the examples. Okay, so let's look at this example. Equilibrium is interesting. We will solve a lot of examples and you get to understand it. So let's take this simple one and see. Two cables AC and BC are joined together at C, and a load of 200 or 2000 Newton is applied as shown in the figure. Determine the tension in the cable. So basically, this is an object. So let's assume an object is at point C and it is being supported by these two cables. And the load has what? 20 or 2000 Newton applied to it downwards this way. We are to determine the tension in the cables. So let's call this cable AC, or tension in cable what? AC. And this will be tension in cable BC. Are we good? So let's look at how we can do it. And remember, this is in what? Equilibrium. There is no swinging. It is what? Static. It is in equilibrium. So we can apply our idea here to get those tension. First, we have two approaches we can use to solve this. So we will look at them. I can use the resolution of what? Forces into component approach. So tension force in this is a force. Tension force in this is a force. And the load here is also what? A force. So I can now resolve them into what? Components. So I'll draw my axis. Remember, this and that, they are what? Alternate angles. So I can say here is what? 45. This is my vertical axis if you want to look at it this way. So this is my X and my Y. The 30 and this place is also what? Alternate, 30 degrees. Are we good? So can we then do resolution here? Yes. So solution 1. First, I'll take summation of forces on the x. And since it is in equilibrium, all summation of forces on the x must be what? 0. Are we good? So I'll take this. It is in the negative direction of the x. So I can say negative tension AC cos 30 degrees. This is in the positive direction plus tension BC cos 45. And this, it is in the what? You can choose any direction because it is on the straight line or it's on the y-axis, plus 2000 cos, what's the angle between this and the any x-axis? 90, which is cos 90 is 0, so it will take care. And remember, we have this as equation 1. So summation of forces on the y2. On the y, we have TB, or let's start with the TAC. TAC is in the positive direction of the y, sine 30, plus we have another TBC, sine 45, and this is in the negative direction, so negative 2000 sine 90. So if we were to equate everything to 0, remember cos 90 here is 0, so to render everything here 0. So first equation, we get negative TAC cos 30 plus TBC cos 45, and this is 0 equal to 0. You take it to the other side because summation of forces on the x for equilibrium structure or particle is what? 0. The same thing happens here. Cos sine 90 is 1. So we can have all this TAC sine 30 plus TBC cos 45. Remember, sine 90 is 1, so 1 times negative 2000 will be what? Negative 2000. You take it to the other side because this is 0. Summation on the y will also be 0, and this will be positive 2000. So we have our two equations here, and we solve them simultaneously. Upon solving them, you see that tension in AC will be 1464.1 newtons, and TBC will be 1793.1 newton. So if you want to use the resolution approach, this will be your solution. What if I want to use the sine rule to also solve for this? What will be my solution? It also has a way of what? Doing it to get your answer. Let's look at it. So let's look at the sine rule approach. So solution 2. Okay, so I will now draw this into what? A triangle. First, I'll have my, so let's look at something. First, we can project this up, this up. We can still have our axis. Are we good? All right. So this is 45. Remember, this is 45. This is 30. So meaning this will be 60 and this will be 45. Are we good? All right. So I'll have my vertical force. I want to draw a triangle out of this so that I can make deduction. I have my vertical side here. Now I have this force, the tension BC, tension AC. So tension BC can be drawn this way. Yes. So this is tension BC. And for tension BC, what angle does tension BC makes with the vertical? 45. So we have our 45 here. And tension AC is also going this direction. So we have tension AC here. And what angle does tension AC makes with the vertical to 60? So we have 60. And using the angle way, we can see that this will be what? 75. Are we good? So using the sine approach, this, remember the vertical one is what? 2000. 2000. So sine rule, I want to find TAC. So can I say TAC on sine the angle opposite to with 45 should be equal to, I have the 2000 on sine 75. And upon making TAC the subject, I'm going to get TAC to be 1464.1 Newton. The same thing if I want TBC, can I say TBC on sine was 60? The angle opposite to that 60, the same thing 2000 on sine 75, and TBC is giving me 1793.1 newtons, and we are good to go. Thank you for watching this episode. We will solve more example and make it an episode so that we will understand the equilibrium of particle very clearly. Thank you.